right? So we have our first exam scheduled. Can I write onto my pen? Oh, that's going to be a problem. My pen stopped working. Okay, so I'm going to talk for now while I fix my pen. Our first exam is going to be March 1st. March 4th. 2 Mondays from now. So the calendar you see on the screen, right? It's the last 2 weeks of February and then the first week of March, right? So March starts on the 1st, but yeah, so this is, this is March 1st. Oh, it works again. Yay. Right. And so here we are here today on a Wednesday. So this is Wednesday. These are Mondays, Tuesday, Wednesday, Thursday, Fridays. Okay. So that's when our first exam going to be. Just while I'm talking about the exam, right? It's an in-class exam where everyone on Zoom, make sure you can find a quiet place and a place that you can have your camera on and also have your mic available in case you need to ask me any questions during the exam. Okay, because that's probably the fastest way to clarify any, any of the questions, because the exam is open book, open internet, open, other resources, just not open each other, right? So what I'll do is I'll open the Zoom and then I will be in a breakout room, and whoever wants to ask me a question can just jump into that breakout room. Okay. Or, people in person can just walk up to me also. Okay. Does that make sense? Let's see. Breakout rooms. Okay. The other thing is that I was going to say, just know that it's a in-class exam for 15 minutes. And those of you who are taking it via Zoom, right, you're going to have to have your scanning software ready, your phone or whatever you're scanning with ready, so that you can actually scan that and turn that in within the 10 minutes between 11:50 to 12, because after that, then I cannot accept the exams anymore, right? Because then who knows what's happening in that, afterward. Okay. So there is a tight deadline for you to scan and upload that if you're taking this on Zoom. Those of you in person will have a printout version of it, so we don't have to deal with that. But those of you online will have to deal with that. Okay. Hey Alex, welcome. Let's see. I think we got everyone online here now. The other thing is that just to give you guys kind of an outlook for the next couple of weeks, right? So here we have today we're gonna try to finish up module 4, right? Either on Friday, right? Finish module 4, which is considering how slowly I'm speaking, that's probably not likely. But so we'll probably have to finish it up the next Monday. Okay, so we'll finish up module 4 here. And I'm thinking to have like a review session where it's like, half me giving you guys some hints on what to expect. And then maybe you guys can come up with exam questions that you can discuss, right? And that might just take kind of like a day. I don't know if that's going to be useful or not. So yeah, Ivan?
Do you think on that day would it be possible to just like go through some example problems from like the homework or some other questions?
Yeah.
Get an idea of how to work out some of the problems.
Yeah, we can. I can go through some of the problems, like how I thought about the problems when I did it, and what's the quickest way to figure things out versus, because the exam is a timed exam, so you have 10 minutes per problem, which is actually the hardest part, right? Because I think given if you since you have the internet and book and everything, given enough time, you can actually solve all the problems, right? But having that time issue is going to be the difference in the exam. Okay. So yeah, so we'll do that. So this is going to be the exam review, right? I don't know if we're going to do this every time, right? But since this is the first one, so just get you guys, everyone comfortable with it. Okay. And yes. Yes, there's 5 problems, 50 minutes. Those of you who had taken my general physics class might have a slight advantage because you've probably seen those type of problems where it's trying to lead you through. So it's trying to lead you, it's trying to give you hints to how to start the problem. and not try to get you to just sit there and think about it for 15 minutes. Because if you think about it for 15 minutes, it's too late already, right? Okay. And since we have the, module 4 being a little bit longer than I thought, and then this midterm review, we're not going to start module 5, right, until the end of technically week 5. So what I did is I just pushed the reading for module 5 after the exam, so you don't have to worry about reading for module 5 at all until after the exam. Technically, you only have 1 day, but but hopefully that's actually helpful versus, because typically the reading for next week is going to be due to this week, right? So the week before, sorry. So so you don't have to worry about module 5 stuff, which is going to be on the Klein-Gordon equation and the Dirac equation, which is the next chapter, chapter 4. Right, chapter 4 in Thompson. Yeah. Yes. So yeah. So the exam covers up to everything for up to module 4, the first 4 modules. Okay. It's good clarification. Sorry I didn't say that beforehand. Okay. Any other questions on the exams? On exam, and what's gonna be happening the next couple of weeks? Okay. So those of you in Growth MSI, or even if you're not part of Growth MSI, we do have our growth seminar this Friday again. It's going to be I think more of a detector person from the Atlas collaboration who's building detectors and testing them. So it's more hardware work. So if you're interested in coming to that, I'm going to send out an email. I haven't got the poster from the LBL people yet, so that's why I haven't sent that out. But I'll get you guys an invite for that. It's 4 p.m. as usual. Friday, 4 p.m. as always. Okay, so seminar. Yeah, always Friday, 4 p.m. for this whole semester. Okay, except the week for APS. Okay. Okay, any other concerns? Oh, the other thing is that there's also some of you guys noted that you're not able to come to the Wednesday office hours. So so the office hours right now, for me at least, right, is Tuesday. What time was that? You guys remember? Oh, 11 a.m. right? And then Wednesday at 1 p.m. But then I'm gonna add a half-hour office hour on Friday, just half hour at 10:30, basically right before class on Friday. Okay. So in case there's additional things you guys want to discuss, I'll try to not work on the lecture right before Friday class on Fridays. Okay. Okay. Any other questions, concerns? Zoom. Okay. Okay. So those of you joining Zoom, I did make a bunch of breakout rooms. Don't join them yet. We're gonna do that in a few minutes here. Okay. After a little introduction. Okay. I think I am recording already, so I'm gonna do that. Okay. So this whole chapter, right, it's all about studying this equation, this gamma Fi, which is the transition rate equation, right? And each of these matrix element, and in this case, this M version of it, right, is the Lorentz invariant version of it, because, right, it used to be TFI, but then what we did was we basically made TFI equals to MFI divided by 2 times the energy with a square root on top of it. So when you square this, what happened is that you get these factors of 2 times the energy of the incoming outgoing particles, right? The incoming one, in this case, we're dealing with a decay of some particle A into 2 particles 1 and 2, right? So this is the incoming particle, EA, and then these E1, E2s are the outgoing particles, okay? And as I said before, right, this MFI thing, right, changes depending on the Feynman diagram we're going to be dealing with. So for example, if you have a tau to decay into it has to decay into a neutrino first, and it spits out W, right? And that W decays into a muon and a muon neutrino, right? That's one diagram, but you can also add to that amplitude a decay into an electron instead, right? So electron, in fact, there's more of these, right? So you can, this tau can decay into also, right? An up and a down quark. I'm not going to try the bars because I have to figure out what the charge is, but this, right, is some sort of hadron, okay, right? In fact, I think on Monday, I was a little confused by the branching ratio of that, and I'll discuss that in a second here, okay? But each of these is a particular decay mode, right? You can actually tell, oh, did a muon come out? Did an electron came out? Did a hadron came out, right? So each of these gives you a partial rate, okay? Each of these, this one gives you some gamma to, let's say to muon, right? This one is the gamma to electron. This one is gamma to some hadron, right? Or however you want to label this stuff, okay? The total decay rate is actually the sum of all these together, right? Because if you have all these possible ways to decay, right? If you add them all up, that's going to be the total decay rate, and that's the one without the subscript, right? Okay. So if you sum up all the different decay rates here, you get the total decay rates of a tau if you don't care what type of thing it decays into, okay? So the ratio of each of these decay channels, right, each of these Feynman diagrams, divided by the total decay rate is known as the branching ratio, right? Think about it as like just, you have one particle and it gets divvied up into multiple different types. A tau can turn into a muon, an electron, and a bunch of different hadrons, right? And this ratio allows you to figure out, well, what fraction of the taus will turn into muon, what fraction will turn into electron, what fraction will turn into hadrons, okay? In fact, you can look these things up on Wikipedia. So for example, for the tau particle, right, the branching ratio for it to decay into hadron, so all of this added up together, right, is about 65%. So 65% of the time it will decay into a hadron, okay? Before I move on, I think on Monday I was kind of confused by this percentage here, where, right, one of the possible ways to do this is that, this, we call this the hadron here. Let's go down to the diagram again, right? Okay. It is almost looks the same, UD. When you clump this together, right, typically an up quark and a down quark, that makes a pion, right? So going to be a pi minus in this case, okay? Okay, but since the tau has 1.7 GeV arrest mass, this doesn't necessarily need to be a pion. This could decay, have enough energy inside it. Typically what's going to be happening is actually have extra angular momentum energy. So these, you can imagine these like up and down quarks kind of like run, spinning around each other. It's not really that, because inside here there's a soup of gluons everywhere. So things are complicated. But, right, another way to have a hadron that's made of a up quark and the down quark is actually the rho, okay? And this rho particle actually has a better chance for the W to decay into, because it actually hits this thing called rho resonance. And because its mass is just right in order for it to have a better chance to decay into a rho versus just a pion. And that chance is about 2.5 times. And so that's why you see this ratio between the rho. So this has an intermediate of decaying the rho, and then that rho decays into these 3 pions, these 2 pions, right? Where the second one is actually directly decaying into a pion directly. Okay. So that's why these percentages there's more complication in them, okay? Because you can make hadrons that have the same quark constituents, but then they are different hadrons because there's different amount of mass energy stored inside the gluon, okay? Right. So imagine this as just, a pion, right? This one, it's not exactly accurate, right? Just like, oh, there's one gluon, connecting them together, right? So that's a pion. But then a rho, right, has more mass, therefore, right, I keep writing pi inside the hadron. Okay. Instead of just having one, it has like, like 100 of these instead. And those gluon has energy in it, and energy gets converted to mass, and then that mass. So this row, I think it has a mass of, if I remember right, like 700 MeV, where the mass of the pion is about 140. Okay. You don't have to memorize this stuff. It's just stuff you look up. Okay. And that's what the reason why. And this row decays into a pi 0 and a pi minus afterward, because it just has enough energy so that it can actually distribute that amongst two rest mass of the pions. It can create two pions because 700 is bigger than 2 times 140, right? Okay. Right. Hope that clarifies the confusion I had on Monday, or if that's even more confusing when we get into the hadronic part of this class, then this will clear up quite a bit more too. Okay. The other part of the branching ratio is, of course, the leptons, right? So they're the muon and the electron, because those are the only two choices for the lepton, right? You don't have more. We only have 3 generations. So if you start off with a tau, it can only turn into a muon or a electron. So each of them contributes about 17%. Okay. And once again, the similarity of these numbers are interesting, right? So like, it's as if muons and electrons are almost the same thing, but not quite, right? There's a slight difference between them. Okay. So when these particles decay, so let's say you started off with 100 tau lepton, right? And you just, stare at it over time, what's going to happen is that, right, if initially you had 100 a tau lepton, they would decay exponentially, right? And that's why the number of lepton as a function of time, so this is the time variable in here, right? It's going to have some exponential decay with it, where it's going to be e to the minus whatever that time is divided by tau, okay? Where tau is known as the lifetime, and the lifetime is actually exactly 1 over the decay rate. And hopefully that makes sense, right? If the decay rate is faster, right, the amount of the lifetime is going to be shorter. Okay, maybe the classical way to think about it, if the students are running out of this room faster, right, the decay rate of the number of students in this class is going to be lower, right, because you have more students leaving per second. Okay. Right. And this is where it takes us into this group activities, where I just wanted you guys to make this plot, so it hopefully helps you guys understand what this means. Okay. Okay. So let's go into, I made 5 breakout rooms, and those of you who are here in person, if you can each jump into a different breakout room. Oh, there's actually 6 of you. Oops, I forgot about. Okay, I'm going to close out the room and make 6 instead. Recreate 6. Okay. If each of you who are here in person can jump into a different breakout room, and those of you who are at Sonoma, don't go into the same breakout room as those who are are also at Sonoma, right? You can join the breakout rooms, but before you do that, take a picture of this photo here, of the screen here, and that way you know what the activity is going to be about. Okay, I'm going to try to move this out of the way. Close. Right. So take a screenshot of this. Okay. What I want you guys to do is just make a plot of this tau decay, or some decay. It doesn't have to be tau. Okay. And then we're going to convert these lifetime into transition rate, right, which is the sigma thing. And we're going to try to calculate some partial widths out of that too, just so we can get some practice with these. Okay. All right. So let's see if we can do this in 15 minutes, and then we'll come back and keep talking about two-body decays afterward. Okay. I'll stop recording.
Do you want to